What is glare and how to remove it? We're going to be talking about ambient glare and machine vision glare, why they're causing problems, and the best ways to go to remove them from our machine vision system. So to start, some of the topics I talk about today are kind of basic principles of machine vision lighting when I talk about reflection and scattered light and direct reflection. If you're confused by kind of the topics that I go through as I talk about them today, I encourage you to go to our webinar. It's on our webinar series, Basic Lighting Principles, on our YouTube channel, the CCS Inc. YouTube channel. And there we'll talk about the basic lighting principles of machine vision, bright field, dark field illumination, capturing the correct reflections. So kind of the basic steps of this presentation will come from that. So I'm going to talk as if we're all on the same page there, but after this, if you feel like you need a little bit more explanation, please check out that webinar and that series. And that YouTube channel itself just has a lot of resources to kind of help think about how we provide lighting in our illumination systems and the best way to do it and how to pick the right light. That being said, I'll get back to talking about glare. So it occurs when there is an unwanted direct reflection off the workpiece to the camera. So light shines down, hits our object surface, and reflects. Oftentimes it scatters, and it scatters in every direction, so we get a very uniform illumination. But sometimes it also has a direct reflection, which means it hits our surface and reflects at the exact same angle that it shines down, it reflects off and oftentimes into the camera. And that unwanted reflection is what our glare is and is what causes the problems. So what causes glare? You know, sometimes you'll be doing machine vision inspections and sometimes you'll have a workpiece that has a lot of glare in it, and other times you won't have to worry about glare at all, even though you're using the same light or you're in the same lab, something like that. And the first and foremost, it's the reflectiveness of the workpiece that is the problem. So if your workpiece is really diffuse, kind of paper-like material, really matte, it's going to diffuse the light in all directions, and there's not really going to be glare because any light that's shining on that sample just scatters evenly. But if you have samples that are more reflective or made of plastic, or they have some type of coating that is shiny, or they're like a metal material, those have much more reflective properties to them. They will shine that light back up and into the camera, that direct light. So if your workpiece is really reflective, that's when your glare is going to become a problem. And it can come from the ambient light, the environment around can be the light that your workpiece is reflecting, or even the machine vision light itself can cause reflections that we don't necessarily want it to. So what happens if we have a lot of glare in our machine vision system? We get images that look like this right here. We get really bright spots of overexposure, and then the rest of the image is a good exposure that would be a consistent way to read the package. And sometimes the glare comes in the way the sample is built. It's going to be in the same place every single time. And then sometimes in certain packages like this, if it's food and beverage packaging or something like that, it can be inconsistent where the glare appears from sample to sample. And when this happens, it makes it really hard to have consistent machine vision imaging and can cause a lot of problems, like incorrect measurements. If you're trying to measure the size of something, if there's a hot spot on the end, you can't find that line as easily as you could if it was just a clean, crisp image. Or if you're trying to do OCR or barcode reading, it might be easy to do in an image like this to read this barcode, but the next sample that comes down, there could be a big hot spot here and we can't read that barcode. It also can misclassify parts. Sometimes it could cause you to let bad parts through, worst case scenario, or the other not great is to not let good parts through, and you're kind of wasting material in that regard. But a lot of times it just makes it impossible to pattern match. Most of the time your machine vision programs, they start with locating the part in your field of view. And if the glare doesn't allow that pattern match to work effectively, the rest of the program's not going to work because it's not going to line up properly on the part, and it can make your machine vision system almost useless if it can't locate the part reliably every single time. So glare can be a really big headache of not letting your machine vision system work properly. So I'll talk about kind of the two ways to remove it depending on which type it is, and we'll start with ambient glare. So what it is, how we're going to remove it, and which method works best. So ambient glare is glare caused by the environment, the light shining around our machine vision system. Sometimes it's just a natural window, if there's sunlight coming through, and this one is extra fun because you'll have, Tuesday, it's cloudy outside, you don't have a problem, everything goes great. But Thursday, it's a really, really beautiful, bright, sunny day, and now your machine vision system isn't working. And if you're not aware of the glare problem, you're not really sure why it works on Tuesdays but doesn't work on Sundays. And that kind of creates a headache as well. So natural, windows nearby always can be a problem. Overhead lighting, in general, you have to illuminate the area for your operators to do their work, but if that causes a problem in the machine vision system, that doesn't mean you can just remove the, turn off the lights, remove the ambient lighting, because it's necessary. So we have to find ways to remove the light for our machine vision system, but not for everybody else. And even it can come from reflections from nearby surfaces. We've had some applications, and by some I mean like one, where the light was illuminating down, that our machine vision light, and it created a good image. When we had it set up in the lab, there was no glare. We recommended the light. The customer installed the light in their machine, and they were getting a lot of glare that was causing problems that they couldn't get around. And what was happening is the light from the machine vision light was reflecting off the shiny materials on their machine and going into the vision system and causing problems. So that's not something we would have been able to predict in our testing lab. We don't have shiny parts around our testing stations, but something that they came across once the system was implemented in their space. So when that happens, how do we remove it? There's three ways that are kind of listed by most effective to least effective. So we've got shielding the light, the intensity of the light, and the filters. So first and foremost, shielding the light. This is kind of the best method because essentially it's removing the problem altogether. If you can just place some type of shroud that blocks the light from getting to your machine vision system, then you're removing the glare issue, you're not letting it get through to your camera, and it just kind of makes it solves that problem for you pretty easily. So you can see here on the left I have an image with the shroud. There's no glare, and the image here I have with the ambient light, there's a really big hot spot. So this shroud doesn't have to be anything fancy. To get this image, I just held up a cardboard box that I had nearby that blocked the light from getting to my sample. Where shrouding can kind of have its pitfalls is if there's lights in many directions that are causing problems. In this scenario here, I just have one light shining down. One shroud is very easy to do. But if there's ambient light from all over that's causing an issue, now you're talking about shrouding your whole machine vision system. If that is possible to do on your line, it's definitely not a bad thing. It is a great idea because it removes the variable of your environment, and then anytime you have to troubleshoot, you're focusing only on your machine vision system alone. You're not dealing with a cloudy day on Tuesday and a sunny day on Saturday. But sometimes, based on how your machine is built, that's not entirely possible to add a shroud in every direction or perfectly shroud the environment. So then we kind of have to move on to other methods after that. In the scenario I talked about where there was light reflecting off of the machine, the way that they handled that was they found a matte material that they put over the reflective parts in their machine. So instead of it being a shiny chrome, they put like a matte black paper around it. So that black absorbed the light, diffused the light, didn't have such a strong reflection, and it was removed from their vision system altogether. So stopping the reflections by removing it or putting some type of dark way of blocking the light from getting back is, like I said, the best most reliable way because it can just remove the variables altogether. If that doesn't work and you don't have the ability to shroud so much, or there's just the way your machine is built, a shroud would get in the way of the rest of your machine working, then we move on to other options. And the next one is using a higher shutter speed. So if you have your shutter speed and you're getting ambient light causing a glare, essentially our camera has an exposure time that is long enough for our ambient light to shine down onto our sample and reflect off into our camera and cause a problem. If we can take that exposure time that is long enough for that process and reduce it, then we're not having it be on long enough for the light to come down, reflect, and go into our camera. But in order to reduce our shutter speed so much, we need to increase the intensity of our light. So what essentially we're doing is we're overpowering the ambient light by making our machine vision light more intense. If you know you're doing this right is if you have your camera take a picture with your machine vision light off, it should be dark. If you're still seeing light, that's kind of the ambient light that you're going to have a problem with. But if your image is dark when there's no machine vision light on, then you don't have it on long enough for your ambient light to be a problem. If you're, kind of easiest example, your light's at 50% and you can just turn it up to 100% and then you can have your exposure time at that short that new short time you need. But if you're already at 100% and you still are needing more light, then you're going to need to overdrive your light. So what overdriving does is instead of having your light on for 500 milliseconds at 100%, you turn your light on at 100 millisecond at 300%. So we're having it on for shorter amounts of time, but at a significantly higher power. So this is going to be a good way to remove the glare that's caused by ambient light, because our light is going to be the only light that the camera can capture, is the light that we purposefully want there. So you can see in this image here, I've got a lot of these kind of glare hotspots. And, is this fully impacting the presence absence of the label or something like that? No, I could probably still have a machine vision system with this included, but just for consistency and for getting a good image every single time, we do want to remove it. So in this situation here, all I did was increase the intensity of my light and decrease the shutter speed of my camera, and I was able to remove all of this glare here. So in these images, I have a red light shining down. I have a red filter on my camera, a polarizer on my camera, a polarizer on the light, and of course ambient light. So I have a red filter on this camera, and I'm going to talk about why, because that is our next method of removing glare. So if we, have a red light shining down, our red light is going to emit at between 600 and 650 nanometers. So that's all of the light coming from this light is within this little, window here. Our white LEDs are going to have a much broader spectrum. This is the spectrum of a white LED. And so what we want to do by adding a filter is we're essentially saying we're only going to let light into our camera that is between 600 and 650 nanometers. So all of our red light from our machine vision system camera is going to pass through the camera with no problem. But with this white ambient light here, we're now blocking 85% of the spectrum, and we're only letting through a small window of about 50 nanometers. So this is going to reduce the glare, but because we're still letting about 15% through, it's not going to remove it fully. So you can see in this picture here, I have a red light shining down and just a little glare hotspot and nothing else. But when I add a red filter to my lens, I'm reducing this glare. The intensity dropped drastically. This would probably be a manageable image after that, but it's not fully removing that hot spot like it is in other scenarios. So adding a filter will help, but the kind of pitfalls of the filter are if you already have a white light set up and you can't change it, then you don't want to add a filter, because you're going to significantly reduce the intensity of your own light, because you're essentially going to be reducing the intensity of your machine vision light by 85%, which we don't want to do. So if you have a white light, this isn't a good option. If your sample has a color to it, you can't necessarily just put on a colored light, because that will change the image, which again, if that doesn't make sense, I go look at our webinars in our machine vision lighting principles series. We'll talk about how color affects images there. So if color is a problem in your machine vision system, then adding a filter doesn't really help. And even so, it works well. It's good, not great. So kind of what does work best? Which option do we want to choose? And like I said, I talked about it in best to worst in a way. So your shroud is going to be your easiest and your most reliable. You're removing the variable altogether. So your only concern after that is just what the machine vision system is doing. If that's not possible, then you want to go to a faster exposure time, especially if multiple lights are kind of causing an issue. You don't have to shroud the whole area. So this is easy. If you just overdrive your light, reduce your camera exposure time. And then adding a filter is kind of your next option. As I said, it only works if you can use a colored light. And oftentimes we'll use it in synchronization with the high exposure time, like that image I showed before. It had the red light filter, the polarizer, and a high shutter speed. So those are the three ways that we kind of can work with the ambient light and remove it from our machine vision system. If after doing all of these steps you still have glare in your system, then more than likely that's coming from the machine vision light itself and not necessarily your ambient environment. So when that happens, what's causing that, how do we remove it, and what is best? So when it's light caused by the machine vision system, it's a glare, it's a reflection that's coming from the light itself. And this can be, maybe the type of light we have, the position of the light, and then the reflectiveness of the workpiece. So I know when I said before that glare is the unwanted direct reflection, and right now I'm going to talk about why I bolded that word and included it, because oftentimes we are purposefully trying to capture that direct reflection to get what we call a bright field image. So our light, in this scenario, our light shines down, reflects off our surface, and all of that light is reflecting into our camera. So that's what this very bright background is. It's capturing all of that direct reflection here. And this dark text is causing, or is appearing dark because when this light is hitting that embossed text, that light is scattering. And so less light is shining up and into the camera, therefore it's not reaching the camera and it's appearing dark. So direct reflection isn't necessarily the problem when it comes to glare, because sometimes, we purposefully want that direct reflection. It's when we're trying to capture the diffuse reflection that we're accidentally getting direct reflection, that's the glare. That is the issue. So how do we remove it? We can diffuse the lighting, we can change the angle, we can use a dome light, and we can use a polarizer. And, in ambient light, I talked about kind of best to worst. Here I'm talking about least effective to most effective. So diffusing the light, essentially, that's just adding a diffuser, and that changes the emission angle and widens it, so it spans out into a larger area. So for more reflective samples, this will improve the glare, but it doesn't necessarily completely remove it like other methods will. A good way to kind of highlight how well a diffuser works, I have a metal part here, and I've got an FE Flex bar light shining down. And if I have the no diffuser option, which is just the clear window, it's going to be more intense because all of my light is, more of my light is being directed to the sample. But you can see I have these shiny spots here, this glare of all of the individual LEDs showing up on my sample. So to get rid of these LEDs showing up, I add a medium diffuser. So this is their semi-diffuse window, which is the diffuseness of a standard bar light. And you can see that it definitely improved the sample, but there still are these LEDs shining that are just causing a little bit of hotspot, like a little less uniform of an image. So then I can step up to my opaline diffuser, and that's more the diffuser level of a backlight, which needs to be extremely uniform. So you lose the power of the light because you're diffusing it much more. You don't have the same intensity, but you have significantly more uniformity. I don't have those LED lights shining anymore. It's a much more uniform image. So having a diffuser will, help a lot in certain scenarios, but it doesn't necessarily guarantee that it will remove the glare altogether. The next option is to adjust the angle of the light. So in this scenario, I have the light shining down, it hits my surface and reflects up into my camera, and that's what's causing my problems. So if I just change the angle of my light slightly, I'm still capturing the scattered light the same way I was in this scenario, but now that direct reflection is going away from my camera, it's not causing that problem, and I'll have a much more even image. So a good example of this is looking at a plastic bin, and I have two bar lights shining pretty directly down onto my bin, and you can see there's a really big hot spot of inspecting the sample. It would be hard to do, whatever inspection we're trying to do on this. But if I take the angle of my lights and I widen it, so I widen that angle of reflectance, and now I'm only looking at that diffuse reflection, and I get a much more even and uniform image that's going to look the same every single time. So that's, going to work for some applications, especially if it's like a flat piece that's just a little bit reflective. That's kind of going to be when changing the angle or changing the diffuser is going to work the best. Where this doesn't work as well is if you have pieces that come through that are packaging, food and beverage packaging, or pharmaceutical packaging, that something like a bag of cheese, the way the bag lays is going to be different every time it goes down the conveyor. So while it might be an even image in one example, and there isn't any angle of reflectance into my camera, at the next piece that comes down might have that perfect angle where it does reflect the light back into my camera, and the next image might have glare the next sample that comes down. So when that's the case and we kind of have more inconsistencies in the parts as the parts come through, that's when we need to go to a different type of light altogether. So that's when we want to talk about using a dome light. So what a dome light is doing is essentially creating that bright field image I talked about a few slides ago, where we have the light is providing a diffuse light from all directions, and so therefore we're putting direct reflection everywhere. We're capturing all the direct reflection. There's no unwanted direct reflection because we're capturing all of it. So we're essentially, like I said, creating that bright field image. One thing with the dome light is it will remove 3D textures, so it will create a pretty flat, ideal image with no glare. This image here was taken with an LFX V200, and this is the same sample I had in the beginning when I showed what glare was and why it was a problem. There were hot spots kind of all over, but with this flat dome light at a really short working distance, we have no glare and a very even and uniform image. There are kind of just a few things to touch on when talking about dome lights. And the first one I'll touch on is the size. And we call this the W theory here because of the way the reflections work. The more reflective your part is, the more this comes into play. To get an even image when it comes to the area that we need to expect, we need to make sure that we have light shining down at the same angle it will reflect into the camera. So in order to have light bounce off the edge of the piece and into the camera, it has to shine from that same angle from the light. So the light needs to be about roughly, based on that, 2 times larger than the area itself. This can be reduced based on, maybe even it has to get bigger based on the working distance of your sample or how reflective it is, stuff like that. So it's not every time it has to be 2 times the field of view, but it's definitely a place to start, and usually it's around that size when we're solving applications like this. Here's an example of a shiny piece of a 200 by 200 millimeter flat dome light. You can see exactly where my light is too small. So in order to solve this application, I would need at least a 500 millimeter light to evenly illuminate this workpiece. Other types of light we have, so the dome lights that we have are the HPD2, the FE flat dome light, and the LFX-V. So the kind of difference between these is how the light illuminates from the light itself. So the HPD2 is your standard dome shell, where it's got that shell, the LEDs shine up, they reflect off of a diffusive coating and shine down onto the sample. It's a very uniform light, very, very diffuse. And then next from there is the LFX-V, where the light shines in to a light guiding plate that has little dots that direct the light down. Also very diffuse. Both of these lights typically need to have, especially the LFX-V, a shorter working distance for the most diffuse results. And then an FE flat dome light is essentially a backlit backlight with a camera hole in the middle for the camera to look through. So you can see in this Raman packet here, both of these give even images, but there's a little bit here where the dome light is giving us a little bit more even illumination on the edge here than the soy sauce gives. And that's just the nature of the dome light is a little bit more diffusive than the flat dome light where that's shining straight down. Honestly, probably if I had a bigger flat dome light, I wouldn't have this problem right here. And this I only had 200 by 200 in my lab. So, picking a light, do I want the HPD2, do I want the LFX-V, do I want the FE flat dome? You kind of have to optimize it between your light working distance. If you can get really close to the part and it's a pretty small field of view, the LFX-V is going to be great at removing glare and flattening your image. If you have to be further away, you have a really large part, then you kind of go to the FE flat dome. If your sample doesn't have a lot of reflectiveness and you won't have the issue of the camera hole, you can use the HPD2. So those are kind of how we pick a dome light. One benefit of the FE flat dome light is you can add a polarizer to it. So this is my segue into the next technique of polarizing the light to remove glare instead of changing the type of light we have to a dome light, which is creating a bright field image. So now to talk about polarizing. So this is for glare that's caused by uneven workpieces and machine vision lights. When light emits from a surface, the wavelengths shine out and they rotate in all directions. They're vertical, they're horizontal, they're 0, 1, 2, 3, 4 degrees shining out of that emitting surface. If I add a polarizing film to my light, what I'm doing is I'm now saying, okay, this vertical polarizer is only going to let vertical light through. So all of this vertical light is passing through. It's blocking every other direction of light. If I add another vertical polarizer, I have vertical light coming, meeting this polarizer, and continuing to pass through because it's all vertical, everybody's happy. If I rotate my second polarizer to be horizontal, what this polarizer is doing is saying, okay, I'm only letting horizontal light through. I don't care about anything else, only horizontal. But this first filter here is blocking all of my horizontal light. And so the second filter here, there's no horizontal light to pass through. So no light actually gets through these two filters when they're perpendicular to each other. So taking this idea and putting it into our machine vision systems, how does it work? What are we doing? What are we capturing and not capturing? So as I said, when light shines down, it emits in all directions. And when it reflects, that direct reflection is also in all directions. And when it scatters, that scattered light is also in all directions. So light shines down in all directions, it reflects in all directions. When we add a polarizer to our light, a vertical polarizer, we have light shining down, and that direct reflection will maintain the direction that it's shining. So it continues to be vertical as it directly reflects into the camera. So if I add a polarizer to the camera that's in the same direction as my polarizer on my light, my vertical light shines through, it reflects, it hits my polarizer, it's in the same parallel orientation, that vertical light shines through, everything is exactly the same. But if I take my light, or my polarizer, and I rotate it to be perpendicular, so now it's 90 degrees from the polarizer on my light, I have that vertical light that shines through, the vertical light reflects, it hits that perpendicular polarizer, and no light gets through to my camera. You might think, okay, well, won't our image be dark if no light is getting through? And that's not what happens. And this is because when light shines down, the scattered light goes back to its original state and reflects, the scattered light reflects in all orientations, all directions. So when I have my, my perpendicular polarizer here, the light shines out, and it's now blocking all light except for that's not that's horizontal. But because I've got my scattered light in every direction, the horizontal light passes through, and we can actually see our image. So you can see in this picture here of the puppies, I have direct light from my ring light above. You can see each individual LED. When I put a polarizer on the light and a perpendicular polarizer on my lens, that's when I'm removing that glare altogether. So this next slide here is a video of the polarizers on my light, on my lens, and all I'm doing is spinning my polarizer to be perpendicular and parallel. So now it's perpendicular, all the glare is removed, and when you see there's a big bright hot spot, that's when it's parallel and all that light is getting through. So kind of one thing to note, which you can see, if I can, I won't play it again, but the polarizer can block a lot of light from getting through. When it was not polarized, it was a very big hot spot. My image was very much oversaturated, but now that all that light is blocked, this is a pretty almost too dark image, but there's a lot of contrast between the text. So that's kind of the downside of the polarizer, is it does lose a lot of light since you're blocking so much of it. So if light isn't an issue, this is a great answer. But if you're struggling for light, it might not work as well to use a polarizer. And kind of one more thing to note on a polarizer is back to this kind of bag where, this was my bad example of glare. My LFX V light gave it a really flat, uniform image. Here's it with a polarizer, and you can see it does a great job of removing glare, but it's not necessarily perfect. You can see there's still a little bit of glare here and a little bit of glare here. So sometimes a polarizer will do 99%, but it doesn't quite do 100. And most barcode readers could probably still read this, definitely could read this, so this could still be a good option for your machine vision system if you can't get a dome light close enough. Close enough whatever, but that's kind of the pros and cons of polarizer there as well. So what works best? I went through 4 methods of removing glare caused by machine vision light, and these are kind of listed out in, like I said, least effective to most effective. So diffusing the light will reduce the glare, but can still leave kind of hot spots a little bit. Might not be perfect, but if it works, then it works well. That's the same with changing the angle. It kind of depends on how reflective the sample is, if there's a lot of shape to the sample, where the glare is coming from on the sample. If it's the same shape every single time, especially if it's flat, this is probably going to be work well. But if it's packaging where one could be pressed one way in one sample and then the next sample comes down, it's pressed a different way, then that might not work as well. A polarizer is great because it will remove glare, especially if it's in a consistent spot or the sample is consistent. But it's not great if the sample is different or for high-speed applications where you need a little bit more light. And then a dome light will solve the problem. It creates that bright field light, but it does flatten the image. So if you're trying to see height changes, it's not really going to work for that. And it does have a little bit more restrictions on the light working distance where the light needs to be placed. So it sometimes doesn't always work in every machine. So really, we want to try and test all of these and make sure that we're not, having the wrong setup and then having to fix the situation later, we want to know what we have to do before we get into our system. So testing all options is always the best way. So those are kind of the, the two ways that we talk about glare, where it comes from, how to fix it. But there are kind of other things to consider, and that's post-processing algorithms. So a lot of cameras these days will have HDR capabilities built in. So what HDR does is it takes pictures at multiple intensities of the light. So one will have a really bright light where there's maybe a lot of glare, and then the next image it takes, the light is dimmer, so there's less glare, and then the last image, it's really dark, so there's no glare, the glare is less intense, but you can't see any of the other things. So you can, combining these images into one gets the HDR image. So what it does is it takes essentially the best pixel of the whole picture and combines it into one flat image. So I don't know if I did a great job explaining that, but what you need to know is it's taking multiple images, combining the best of each of them into one image to get one evenly illuminated image with less glare. The other option is using computational imaging or shape from shading. When you use shape from shading, you get two images. You get the shape image and the texture image. So what this is doing is it takes a picture from the north, the south, the east, the west, and then once again it's kind of taking the best pixels from each one and combining them into one image of removing glare. So that's what this example is. This is Q-tips in plastic packaging where there's a lot of plastic overlapped here. There would be a lot of glare. You can still kind of see it even with this texture image, but this would be a very easy barcode to read using it. These two options, they work. The kind of downside to them is, you're taking multiple pictures, you're combining pictures, so your processing time and your, time it takes to get each picture and the result is going to be longer than just solving the problem from the lighting standpoint. And, the effectiveness may or may not work on everything. So, if you want to try it, I won't say no, but there's definitely other ways that I just talked about that might get you the same results that are faster and a little easier. AI imaging I have here, I'm not 100% sure how much it's doing for glare at the moment, but honestly, we don't really know for AI imaging, so eventually it might solve our problems altogether. I'm not sure, but it'll be interesting to see what AI imaging does to the future of machine vision. So if you are doing testing in your lab, I kind of said a few slides back that it's really important to test every single orientation, just to make sure you're getting the best image that you can get. You want to make sure you have the right items in your lab to test every type of method that I just discussed. So kind of the suggestion that you need a light you can overdrive, you need some type of dome light, high precision lights that can get you a bright field image, a way to overdrive the light, and then a filter kit. So in terms of a light you can overdrive, the FE Flex bar light is great, and the ring light, if you get the kit version, it comes with all of the diffuser windows I talked about, the transparent, the semi-diffuse, and the opaline. And then you can also get the polarizer accessories along with that. And then light you can overdrive, most all of the CCS high precision lights can be overdriven as well. In terms of a dome light we recommend, the LFXV, if you have any takeaway from this PowerPoint at all, or this webinar I guess, I would say having an LFXV light in your lab is probably one of the best lights you could have outside of your kind of standard ring light, bar light, coaxial light. Actually, it's probably better than the coaxial light. It solves a lot of applications that I wouldn't have otherwise been able to solve. It just does a really good job. I use it a lot, and it just provides a really good even illumination to remove text, remove glare, or remove height changes, remove glare, along those lines. So maybe your biggest takeaway is to get the LFXV in your lab. But the FE flat dome is a good one to have. If you're going to get it in your lab, I recommend maybe getting a little bit larger than you think you might need. Kind of going back to that W theory, if it's only 200 millimeters and you're kind of limiting yourself to 100, 200 millimeter field of view versus if you can, have a 300 or 400 even, then you're kind of giving yourself a little bit more ability to test larger field of view items. And they also have a polarizer kit that you can add to this flat dome light as well as an accessory. And the HPD2, I would get the LFXV over the HPD2, but it still is a good, useful dome light that can solve a lot of problems as well. And then the specific CCS high precision lights, the LDL2 bar lights are always really flexible. You can get diffusers and polarizers for those. The LFV3 is our coaxial light. That's a good one for creating a bright field image and still kind of being able to see those height textures at a larger working distance. And it also has diffusers and polarizer accessories. And then our ring light, the LDR2, which is how I solved a lot of the polarizing applications throughout this PowerPoint. There's a diffuser option, a polarizer option, and then you can have an adapter that attaches those two to the light. If you're an overdriving controller, we recommend Gardasoft for the CCS lights. The FE-Lux lights actually have overdriving built into them, so it kind of just depends on how you trigger the light and how you set up the pins. But for any CCS light, Gardasoft controller is great for overdriving. And last but not least, I do recommend that all labs have a good filter kit. And this is, in terms of machine vision glare, you really just want that polarizer out of it, or to put on the red light filter for the red light to block out that glare. But just in terms of lab use in general, I love having a filter kit because I don't always have the right color light in the right size. I'll have a red coaxial light that's 100 millimeters, but sometimes I need a 200 millimeter red coaxial light, but I only have it in white. So in that scenario, just to make sure that I'm getting a good image, I'll put my white light I'll use that in my system, but I'll put a red filter on my lens. And I wouldn't recommend this as a solution to my customer of buying a white light with a red filter, but at least for my testing, I can see, okay, I do want a red light because what that filter is doing is it's blocking all other wavelengths except for red, so it's effectively creating a red light for me at just a really low power. So now I know I need this size light, I know that this color works, and I was able to solve this with a white light. So having a filter kit is great for, like I said, removing glare, your polarizers, but also for just general testing. If you have all white lights in a filter kit, that's essentially the same thing as having red, green, blue in every light size. And then you can, once you buy your red light, you can still put on that red filter on your lens just to help with ambient light as well. So in summary, we have ambient light, glare caused by our environment. The best way to get rid of it is to shield the light. Otherwise, you can increase the shutter speed and decrease the exposure time. So we're overpowering the ambient light. Decrease the we want to overpower the ambient light with our machine vision light. And then last but not least, add a filter, which will, if you do that step alone, it will help but not work 100%. If you do it in parallel with increasing the shutter speed, then it'll have a lot more of an effective result. If it's glare from a machine vision light, you want to diffuse the light and or change the position of the light. This is kind of sample dependent, not going to be the best. It's not going to work every single time, but for a lot of samples it will work, and it will work really well. But if that doesn't work, then you kind of go to dome light or polarization. Those two, I wouldn't say that one works 100% better than the other. You don't want to always do dome light and never do polarization, or always do polarization and never dome light. That's a lot more sample dependent on which one's going to be best. So having both options in your lab to test is going to be just ideal for making sure you have the right solution for all of your machine vision lights. So kind of with that being said, that's all I have about machine vision glare today. If you guys have any questions, feel free to type them in the chat now or shoot us an email later. This will be posted on our YouTube channel for you guys to reference back. And like I said, all the other webinars are there as well. So tune in for next year. This will be our last webinar of 2023, but we have a few more planned in 2024, so be on the lookout for those registration links as well. But thanks for all who attended and stuck around this long. Yeah, happy holidays, everyone.